All right, guys, so take a deep breath. We go with Clairaut's theorem. So Clairaut's theorem, really what is it saying is, I'll first just introduce it for suppose we have a function from R2 to R. And then we say the following. D squared f, the mixed partials, dx dy, at the point AB will be the same as d squared f dy dx at the point AB, provided that the mixed partials there are functions from R2 to R are continuous in a small disk centered at AB. So the picture is, this is AB. And this is the disk, and inside of this disk they have to be continuous. It could be microscopic. Okay? So let's prove that. Proof. So first let's consider what's the mixed partial d squared f d x dy at the point AB. Let's consider what it is really. This is the same as the partial derivative d dx of the partial derivative function df dy at AB, which by definition is limit as h goes to 0 of the partial derivative of f with respect to y at the point a plus hb minus the partial derivative with respect to y at the point AB divided by h. So far you understand? This is just the definition of the partial derivative. This is just a function, and I'm just taking the partial derivative with respect to x of that function. So far good? So now I'm going to expand it a little bit more. It's going to look a little bit uglier. So what is this? This is limit as h goes to 0 of, now I'm going to look here. What is this here? This is just limit as k goes to 0 of the function f at a plus h, b plus k, minus f of a plus h, b over k, minus, I'm pulling the limit out a little bit, so I'm just applying it here as well. So here it is f of a, b plus k, minus f of ab over k, divided by h. So far good?
No, can you explain that? Why you did it?
I mean, I'm just, what I do is I just expand this limit. So first of all, I just looked at it as just the derivative with respect to x of some function. I forget for a moment that it's, again, a derivative with respect to y. So expanding this, by definition of partial derivatives of any function, it's this. Okay? And then each of those segments, I'm expanding again in terms of what they are in the limit. So then if you pull out things and simplify, what is this? This is just the limit as h goes to 0 of the limit as k goes to 0 of the following expression. I just kind of do some algebra. Basically, I move the k down. And in the algebra, what you get is f of a plus h, b plus k, minus f of a plus hb, minus f of a b plus k, minus f of ab. And all of that thing, all of that ugly thing, divided by...
Is the last term a plus because it's minus the second?
Plus, you're right. Thank you for noticing. That's good. It's a plus. Right? Divided by h times k. Okay? This is what we get for that definition. Okay? So it's very... Let me just write on this board. Did you copy this? Do you remember that they are continuous? I just have very little board. I would have preferred to keep it because this is very important. We're going to use this. I actually don't think that that continuity is necessary. I think you can loosen the hypothesis. It has to only be continuous on lines, I think. But I have to verify that. I think you only need continuity on lines. But for our purposes, we'll just assume we have continuity inside of a disk. So it's very ugly to write this entire thing, so I'm going to call it by a name. So I'm going to say lambda of hk is that thing in the numerator. Right? So lambda of hk, and this I'll try to keep written, it's f of a plus h, b plus k, minus f of a plus hb, minus f of ab plus k, plus f of ab. Okay, that's going to be my lambda. So with this notation, what I have is that this is just the limit as h goes to 0, limit as k goes to 0 of lambda hk divided by hk. Okay? That's what I get when I expand this derivative. Similarly, so you can do that verification yourself. If I want to take the partial derivative of f with respect to y, first with respect to x and then with respect to y at the point ab, that would be limit as k goes to 0, limit as h goes to 0 of lambda hk divided by hk. Look how similar they are, very similar. If you expand, what you see is it's very tempting to believe that they are the same. What's different is the order of limits. Here, h is first, then k, and here, k is first, then h. You understand? So, I mean, in some sense, you might have just, well, they must usually be the same because it's very simple, very similar. But limits usually cannot be exchanged. You cannot usually interchange limits. So you just want to say, well, just interchange the limits. Usually, that's one major thing in analysis. It does not work. You understand? So I want to prove that I can interchange limits. Need to show that limits can be interchanged.
This is the idea of the second partial derivatives being equal?
Yes, you can see that. Look at it. You already see when you expand them. Look, we expanded this and we got this expression. And if we do the expansion when we take the derivative with respect to x and with respect to y, we get a very similar expansion. So I mean, if you really just if it's too much, you can just right now say, well, let's pretend that you can interchange limits, and that's it. But the thing is, there are examples where they are not equal, which means again, it tells you that limits usually cannot be interchanged. But I made an assumption that the partial derivatives are continuous in a neighborhood of AB. In a neighborhood means they are continuous inside of a microscopic disk whose center is AB. That's going to be an assumption that I'm going to use to make it. So let's try to engineer it.
The point is that if you can prove that the limit of k goes as whatever, that those two limits are actually equal to each other, then you can.
If you can do this, if you can prove that you can do this,
then you prove that they're
then you prove that they're the same, not that they're continuous. You prove that this mixed partial is the same as that mixed partial. Do you see the difference? Look at the difference. Here h is first, then k. Here k is first, then h. So they're already very similar. If you can prove that you can interchange the limits, you have established that they are the same.
Right, but the proof or the theorem included the idea of continuity. And
yes, because again, it's very tempting. It's very tempting to just say, well, just interchange the limits, but it doesn't. It's not true. There would be if you just interchange the limits and say, well, I could have lied to you. I mean, in some ways, in my notes, I just lied to you. I kind of said, well, why are they equal? Because, well, and say, here's what you get, and then just, and that's it, right? But that's a lie, and I feel bad. I'm not a liar, I hope.
No, so I'm saying, where does conceptually continuity fit in here?
We didn't get there. I mean, you're pushing me, you're spurring me too fast.
Okay, I'm sorry.
Right? So all I just said now is that they are very similar. Interchange the limits, if you can, and then you'll see that they must be equal. Right? So this is the work. Now it's hard. Before it was not hard, right? So let me try to show you what you can do. Now you look at this thing, and if you define something, if you notice something appropriately, you can This is the very difficult thing. I mean, to give you an intuition for why you do that. So you look at this. Look at it. It's a plus h, and this is a plus hb. So I'm going to do this and that. I'm grouping it like that, and actually forget about it. Let me just write first of all what I do, and then you might see the grouping. So then I'm going to define a function that I call phi of x. Phi is a function from R to R, roughly speaking, right? It's just a single variable function, and it's going to be defined by phi of x equal to f of x b plus k minus f of x b. So this is something that will take you some time to notice why you do that. So it's f of x, it's this function. So then observe that if I want to calculate so then lambda of hk is simply phi of a plus h minus phi of a. You see what I did? I just see that if I replace this by x, look at it. So this is here. Let me group it. So grouping it this way, this is just phi of a plus h, and this here is when I pull out the minus. This is going to be phi of a. Do you see a and a here, and a plus h and a plus h? So basically, what I do is I reduce I just say that lambda of hk is really phi of a plus h minus phi of a. Okay, I'm reducing it to calc 1 in essence, right? And I'm going to use the mean value theorem. That's really what I need. And basically, the theory of the continuity, all that thing is to allow mean value theorem. But mean value theorem, I think it's actually you can reduce the hypothesis to only continuous on lines because the mean value theorem needs a line. Okay, I'm going to try to draw you the intuition for that. That's a little bit challenging. So this is lambda of hk. It's phi of a plus h minus phi of a. Okay, and let me also define another function, theta from R to R. And that's going to be defined by theta of y. You can actually look at it and also group it in terms of y. So you look at b plus k and b plus k here. So you're going to group it this with that and this with that. Okay? So you're going to group it like this and like this. So phi of y is going to be defined as f of a plus h y minus f of ay. Okay, write it to yourself because I have a very short board. Okay, and then what you have, that lambda of hk is also equal to phi of b plus k minus theta of b plus k minus theta of b. So then here is what we're going to now do. So we're going to now work with the first function. So lambda of hk is equal to phi of a plus h minus phi of a. Now what is this? This is by mean value theorem. Because you see, this is calc 1, really, right? This is a function of only one variable, only the variable x, right? By mean value theorem, this is the same as h times the derivative of this function at some value a star. So here the assumption on a star is that a star is between a and a plus h. I mean, could be between a minus h and a plus h, but basically very close to a. That's by mean value theorem, if you remember it. You remember mean value theorem, guys? No. All right, so I'm not going to pause right now. I mean, just remember it's by the mean value theorem, and I can then explain to you. This is extremely important theorem, or very useful. And you should have an intuition for why it works. So by the mean value theorem, I can do this. Now, what exactly is this? Now, let me just expand this. This is h. What is the derivative f prime of a? So this is just the same as the derivative with respect to x. This is really h times d theta dx at the value a star, which is h d theta dx. Here is d phi dx. It's the derivative of this function. Here it is. It's the derivative of this function with respect to x. So this is h times, in parentheses, the partial derivative of f at x, evaluated it at a star b plus k, minus the partial derivative of f with respect to y, evaluated at a star b. This line. But look at this thing. This is A star, B plus K, A star B. They're the same A star. They are the same A star, which means I can apply mean value theorem again, but this time with respect to y. So again, this is now equal to h times k, where k comes from here, right? H times k. And now this is the mixed partial. This is the derivative, d squared f dy at A star, B star, right? Because really I look at b plus k and b, so it's now again a function of only one variable y. So, and I wrote something incorrect, so it's dy dx, okay? It's hk d squared dy dx of A star b star, where b star is something between b plus k, and b. Okay? Don't worry if you don't understand. I mean, it's something to digest, but I would really, if you can figure this out, you're already moving up to a higher level. At the end of it, I'll tell you maybe some sketch of why is it useful, right? I mean, some sort of things that you use it for. Although usually it's instinctive. I don't really remember what I use what. I mean, I see something, sometimes I say, oh, that might be useful, right? So just instinctually. So look at this thing. We have hk, we pulled it out. So now we have that the mixed partial d squared f dx dy at the point AB. This mixed partial, which we assume exists, is equal to limit as h goes to 0, limit as k goes to 0 of lambda hk divided by hk, which is limit as h goes to 0, limit as k goes to 0 of lambda of hk is lambda of hk is, remember, lambda of hk is the same as phi of a plus h minus phi of a over hk. And then we already established that this thing here is the same as limit as h goes to 0, limit as k goes to 0 of hk, the second order partial dy dx at a star b star over hk. So the hk cross out. And what you get is, this is just limit as h goes to 0, limit as k goes to 0 of the mixed partial dy dx, you see it's dy dx at a star b star. Now what we know this by hypothesis is continuous, right? So by hypothesis it's continuous, and a star is going to be squeezed towards a, and b star is going to be squeezed towards b. So what it's going to be the mixed partial d squared f dy dx at ab. So did I? So I mean, there is a small mistake here. So I should say that limit, I mean, this is not necessarily that. So limit of h going to 0, of k going to 0, lambda of hk over hk. This part, by the way, is slightly wrong, right? So you erase it. Sorry about it, right? Because I just right away assume that this is, I mean, I don't remember how it's set up. What matters is that this limit, if you take this limit when h goes to 0 and k goes to 0, you get this expression, and you get that this is equal to the partial derivative of yx at ab. Okay, so this is 1. And now if you repeat this construction with 2, you can also say that so the hk, they cross out here. So you can also say that I do need it here. When h was going to, yes, sorry. So this is 1, now 2. If I take limit when k is going to 0 first, and then limit as h going to 0 second of lambda hk over hk, you can now use the phi function. So that would be limit as k goes to 0, limit as h goes to 0 of theta of b plus k minus theta of b over hk, because this is the same as lambda hk. It's written there, right? And what you will get is that by following exactly the same reasoning as in 1, what you get is, and here you have to be really careful, this is going to be limit as k goes to 0 limit as k goes to 0 of limit as h goes to 0 of hk, and here you will have the partial derivative first with respect to y and then with respect to x at some a bar, b bar. The reason I write a bar, b bar, then have to be a star and b star divided by hk. And what you get is limit as k goes to 0, limit as h goes to 0 of d squared f dx dy a bar b bar. And by continuity, that we're saying that this derivative is continuous, this is going to be d squared f dx dy at ab. Okay?
Did you have to show the mean value theorem for that thing as well?
Now, what I just showed here is a very important thing that I need to mention, because otherwise it's not clear. What I showed in either of those limits is, look at it, limit, basically this function, if you approximate it, forget about the limits for a moment, if you approximate it, you really get mixed partial here. So that tells you that limit, so that's the important part here. Limit as h and k goes to 0, 0, no matter in what order, of lambda of hk over hk exists. That's very important. It exists. That's something that I kind of should have emphasized a little bit better before. Look at it, right? Forget about the limit for a moment. When you're doing this approximation here, you're just saying lambda of hk is this, and then once you get to this point, you can cross out h and k. So really lambda of hk is equal to the derivative with respect to y, with respect to x, at some a star b star. For any h and k, it's equal to some a star b star. There are variables. They're really functions of h. So here is how we should say. We should say that lambda of hk over hk is equal to the partial derivative of f with respect to x and y. Thank you. At a star of, it's a function of h and k. A star is a function of h and k, and b star is a function of h and k. But the partial derivative, it's a continuous function, but this partial derivative is continuous, right? So because it's continuous, then I'm able to, see, I'm able to eliminate the hk, and I can use the continuity of this mixed partial. That's the subtle point here. Okay? So really, the reason you can, what happens here is I'll try to draw you a picture. So here is, here is AB. So for very small h and k, you're inside of this disk. For very small h and k, you're inside of the disk. And what you have is some point here. This is your A star, B star. And possibly some point here is your A bar, B bar. Okay? So once you're in, once h and k are very small, you can be assured that A star and B star and A bar and B bar are inside of this disk. Once you're inside of this disk, continuity of the partial derivative takes on. Because as h and k go to 0, as h goes to 0 and k goes to 0, should I say that? As h goes to 0, it would force A star to go to A. And as k goes to 0, it would force B star to go to B. Okay? So in the first limit, in 1, how does 1 work? 1 works, first I'm pushing k to 0. So I'm first going like this. Okay? K is going to 0, so you're going like this, and then you're going like this. And for A bar, B bar, I am first going, I'm first pushing, sorry, then I'm first pushing x to 0, or h to 0, sorry, right? And then k to 0. Okay? No, I use the continuity of those mixed partials. They are all continuous at those points, right? So look at it. Once the point A star, B star is here, in the limit, what's happening to A star, B star, right? So look at those limits. If I first push k to 0, then h to 0, then I'm approaching AB along this path, right? But approaching it along this path, by continuity, is the same as approaching along this path. Because the function is continuous at AB, so no matter which path you go to or towards AB, you're going to get exactly the same value. Okay? So once you're here, it doesn't matter which path you take. So if you take this path here and then here, it's the same as taking this path then this path. So that tells you that if you look at it, this path means first k goes to 0, and then h goes to 0. This path is the opposite, right? First h goes to 0, then k. You see what I'm saying? So this is the interchange of limits is allowed here because once you prove that you get a point, once you basically reduce this expression, you just reduce this expression to a partial derivative, a mixed partial derivative at a point inside of the disk of continuity.
Are we trying to say that it's path independent?
Yes, I'm trying to say it's path independent inside of the disk. So it's very subtle, right? It's very subtle, very easy to confuse something here, right? I just did it from, again, I mean from, just, you know.
How do you know how large this could be?
Well, it doesn't matter. Once look at it, right? So I can select h and k to be very small. I can select h and k to be very small so that the point fit inside of the disk. Okay. So let me just say a few more things about it. Can I erase? So think about it. Okay. This is a very subtle theorem. So a few remarks about it. So if a function f is from Rn into R, and I want to consider whether d squared f dxk dxj at some point a is the same as d squared f dxj dxk. I'm only using xk and xj need to be considered as variables. Right, because look at it, all the others are fixed, right? So in essence, so our proof works. So our proof works all the same. So without also basically, I can reduce it to a function from to a particular function from R2 to R, because all the other variables are.
The the equation has the A vector also? The same
Yes,
A vector?
yes, of course. Okay, so the proof would work all the same, because look at it. When I take partial derivatives with xk and xj, those are the only variables. Everything else is fixed, right? So really, the proof that we gave for R2 to R would be generalized immediately to any function from Rn into R. All right, so how is it useful? How is Clairaut's theorem useful? So, applications. So first is differentiation works like multiplication. For example, you usually define some sort of operator. So you can define, let's say, for whichever reason, you need to define an operator by calling it dx plus dy. So dy, right? So this is going to be from differentiable functions, let's say from C infinity functions to C infinity functions. C infinity means infinity differentiable. C infinity is infinitely differentiable. So then what you have is, for example, then if you want to take, the way it's going to work is that as a function, it's going to be d dx plus d dy applied to f. So you see, it's taking a function. So d dx, so it's going to be df dx plus df dy. That's going to be the way it applies, okay? So when you study things, you're going to use operators. So it's going to be just, things are going to be complicated like that. So then imagine that you want, it's by the way a linear map, but it's a linear map from C infinity to C infinity. Okay? So then imagine you want to compose it with itself. So then you can say d dx plus d dx dy, sorry, squared applied to f is really the same as d dx plus d dy applied to df dx plus df dy. Okay? So that's the square. So what is it actually going to be? If f satisfies its infinity, it means that all the partials are continuous. So that would tell you that you can actually just simplify it and write it as d squared dx squared plus 2d squared dx dy plus d squared dy squared applied to f. Okay, so it works like multiplication. You see, that's what I mean. If you take three combinations, if you basically take this operator and apply it 3 times, so that would be d dx plus d dy cubed, and that would just be like expanding a cubic. And that only, if you just look at it, if you look why, this only works for functions that satisfy Clairaut's theorem. Okay. That's one example of where the theorem is applied. So in other words, you cannot say differentiation is like multiplication unless you have Clairaut's theorem. It doesn't work. One last thing. 2. This you might not quite understand is, let's say, conservative fields. So conservative fields is basically that roller coaster example I gave in chapter 2. So imagine that what you have is you have a path from point A to point B. And you have a particle traveling along this path. And there is basically in the background, there is a vector field. So basically the vector field is, I don't know, something like this. So that's vector field. So a vector field, what is it doing? It's really just basically at any given point xy, there is a force, right? There is a force pulling the particle somewhere, okay? And the particle is moving along this point. So the question is, if I select a different path, if I select another path from A to B, let's say here's another path. So we consider basically integrals over the path. So we want to consider the work done by the force as the particle travels on this path from A to B. So I can consider one path is it's the integral over path sigma 1. So let's call this black path is sigma 1. The path over sigma 1 of the dot product of the force. Dot product of the force with dx dy. So the work is going to be the dot product of this force with dx dy. And I want to know whether or not this depends on the path. So in other words, maybe I select a different path, and maybe I will have a different work, right? So that would be sigma 2, the dot product of f with dx dy. So you understand f, it's basically, it's a two-dimensional field, so it's f1, f2, two-dimensional field, okay? So how can I test that? Well, if f is f1, f2, it's usually written pretty much. If you want to, you can write it as sigma 1, f1 dx plus f2 dy. That's the dot product. This is just work. This is f1 dx plus f2 dy. So are they the same as long as the paths have the same beginning and end point? If yes, then it's called a conservative field. Okay? So how would you test if it's a conservative field? Well, what you can do is the test is you take the partial derivative of f1 with respect to y and subtract the partial derivative of f2 with respect to x, and if it's equal to 0. If yes, I mean, there's some other assumptions, but basically if yes, then conservative field. Now why? Because if yes, then you can say that f is a gradient field. So basically the question is the vector field f equal to the gradient of some function? We're going to study gradients in section 2.6. Okay. So the gradient, basically, what is the gradient of f? The gradient of f is just the partial derivative of f with respect to x, the partial derivative of f with respect to y. Now the reason you see, so if it's a conservative field, then it must be, then f must be the gradient of some function f, where f is a function from R2 to R. Roughly again, right? So this has to be f1, this has to be f2. So you see what I'm doing here? Why do I take the derivative of f1 with respect to y? Is because the derivative of f1 with respect to y should be equal to the derivative of f2 with respect to x, because those are going to be mixed partials, right? So derivative of f1 with respect to y will be equal to the mixed derivative df dy dx. Okay? And the derivative of f2 with respect to x should be equal to the mixed derivative d squared f dx dy. And if those functions are, well, if you take the derivatives, you see the assumption that I'm making here is when you take the derivative, you get something continuous, right? So if the derivative of the first component of f is a continuous function, and the derivative of the second component is a continuous function, and it happened to be a gradient field, right? Then it happened to be that we had a mixed partial derivative, and the difference is 0. Okay, this again, don't worry if you don't understand anything at all, right? Don't worry if you don't understand anything. My only point is that, you see, Clairaut's theorem kind of figures in the background. That's all the point, right? And this is a very important problem in some sense, right? Because this involves, let's say, if a force is path independent, should you say that? Then when you need to calculate how much energy is, let's say you're flying, you're moving a roller coaster from this point to this point. You can then use a very simple path to calculate how much energy is going to be spent by moving from here to here. You understand? So in essence, usually taking the integral over those complicated curves is very hard. But if the field is conservative, then I can replace a very hard curve by any curve I want. So I can make a very easy curve. And I kind of explained something about conservative fields in my section in chapter 1.2 on dot products. Remember, I didn't do anything sophisticated. I just kind of showed you that gravity should be a conservative field. So the end result, the end velocity is independent of the particular curve. All right, good.
Does gradient imply this mixed partial derivatives being equal and vice versa?
I mean, there's more to it. I mean, I'm actually just crunching it, right? And hopefully not saying anything wrong. Right? You have to be very careful, right? But my point is that you see that in this test, we're not going to go over this in our class, but in this test, the Clairaut's theorem actually figures. Okay?
I mean, the derivatives are equal to each other, right? Equaling to that.
I mean, this is just a test. I mean, if you understand Clairaut's theorem and you understand some other ideas, then you would see why this is the test. Why do you take the derivative of the first function with respect to y, subtract the derivative of the second function with respect to x, and why do you want to get 0? Right?
Well, they should be equal.
They should be equal if the field is conservative, right? So that's a good test, because really it's very hard usually. Maybe it might be hard to guess what is the function. So you can say if f is the gradient of some function f, then it's path independent. Okay, and you can show that this is the only condition. This is basically vector f is path independent if, basically it's like a fundamental theorem of calculus, if there is an antiderivative for f. And the antiderivative is in the sense that there is a function f, if you take its gradient you get this vector field. You understand? So really that's fundamental theorem of calculus is concerned with antiderivatives. What you studied in Calc 1 is just the one-dimensional idea here, right? It's the one-dimensional idea of path independence. Remember that when you took the integral, you only had beginning point and end point. It's capital, it's subset of f of a minus f of b. So there are generalizations of that. Right, good?
Thank you.
So again, I really hope, I'm a bit tired, I really hope I didn't say something nonsensical. I could have, right? But I tried not to, and this is I just kind of crunched very fast, right? And I actually haven't mentally gone over all the possible hypotheses, right? So I'm hoping nobody's going to say, oh, you found something wrong. Yeah, that's roughly what's happening.
Well, you were caught on tape, so.
Yeah, now I'm on tape. Let's do it.